All right, so we've talked about constructions, and now we're going to learn a little bit more about transformations. And that's some kind of movement of a figure within space. A lot of times we'll look at the coordinate plane. And then we're also going to talk a little bit about symmetry. Okay, so first we're going to talk about rigid transformations. And rigid transformations mean that your shape stays the same size and the same shape. Okay, the shape doesn't get distorted and the size doesn't change at all. So that's what rigid means. It means non-flexible. It stays the same. Okay, it's rigid. All right, so the first one we're going to talk about is translations. And that's basically when you just move each of the points the same distance in the same direction. And that distance and direction is what we call a vector. Okay, so this thing is called a vector, and that is the distance and direction that we're moving the figure. Okay, and you might know the translation as a slide or a shift. Okay. So we're going to take a look at how can we look at that on the coordinate plane. Well, when we have direction here, if we're on the coordinate plane, we can make a triangle out of that. So we're shifting so many units to the right or the left. So we're going to say that's h units. And then how high up or down we're going is going to be k. So if you take this point and you move it over h and up k, you get to the new point. So all that does is add h to your x value and k to the y value. So each of these points, if you know all of the ordered pairs, you're just going to add h to the x value and k to the y value to know where the new point is going to be. So we say that this gets mapped on to this. All right, so if we have this point here, and this was x, y, then this new point right here is x plus h, y plus k. Okay? Now, if we label this point as A, then after we translate it, we're going to call it A prime, because we took that point and translated it. Okay? So we call that A prime because A gets mapped onto A prime. Okay, now let's talk about rotation. Rotations are when you take all of the points on a figure and you just rotate it about some center of dilation. So here, this is your center of dilation, or center of rotation. We'll talk about dilations later. That's not a rigid transformation. So your center of rotation is the point where of your rotation, okay? And then your angle of rotation is how many degrees, how much you're rotating. So you always need some angle for that angle of rotation. So the two things you need for rotation are center of rotation and the angle of rotation. Okay, so if we rotate about this point, then we have a certain number of degrees. And when we take a look at the coordinate plane, if you do a 90-degree rotation, and that's clockwise, if you do a 90-degree rotation, so suppose this was in the first quadrant and you do a 90-degree rotation, you're now going to be, and we're going clockwise, you're now going to be in the fourth quadrant, which makes all the y values negative. So you still have the positive x values, but now your y values are negative. And if we, and now let's take a look at if we rotated it 180 degrees. Okay, so if you're in the first quadrant, if you're going 180 degrees, well, 90 degrees will put you into the fourth quadrant.
Mr. Scott Hunter and Mr. Reister, could you please come to the front office? Thank you.
180 degrees, if you're in the first quadrant, 90 degrees would put you into the fourth quadrant, so then another 90 would put you into the third quadrant, and that changes your x and y's to both negative. So that's 180 degrees, and actually for 180 degrees, it doesn't matter if you go clockwise or counterclockwise, it's still going to be the same, it's going to be the same mapping. So again, if we have this point, and we'll call it B, and it gets rotated this number of degrees by this center of rotation, it's going to get mapped onto this point, and so we call that B prime. So B gets mapped onto B prime. Okay, and that's the symbol for mapped onto. Now let's take a look at reflections. You always need a line of reflection, okay? And so you're just, and these really, yeah. Okay, so you always need a line of reflection, and you're just taking all of these points and reflecting it over, so they're going to be the same distance away from that line of reflection, and it's going to be the perpendicular to the line of reflection. So all of these line segments that map one point onto another are all going to be perpendicular, and the line of reflection is going to be the perpendicular bisector of that segment. Okay, so C gets mapped onto, and this says C sub 1, but it really, usually we say C prime. So we'll make all those prime. And then B gets mapped onto B prime, and so on and so forth. Okay, so you're always looking at the perpendicular to the line of reflection, and then the line of reflection bisects that line segment. So you would just find out how far that is, and then make the new point the same distance away. All right, so let's take a look at some ordered pair rules for when we do reflections. And there are three that we're going to use often. We're going to have a reflection over the y-axis, that's the vertical one. We're going to have a reflection over the x-axis, that's the horizontal, and a reflection over the y equals x, and that's the line that cuts through the coordinate plane like that. Okay, so when you reflect over the y-axis, that's going to change all of your x values to negative. Your y values stay the same. Okay, so now you're going to have negative x and y. Okay, and then when you reflect over the x-axis, okay, if you go back to the original, if you reflect over the x, that changes the y to negative. So now we have x, negative y. And then if you reflect over the line y equals x, that one's going to switch your y and x values. All right, now the last one we're going to talk about is a non-rigid transformation, because while it doesn't change shape, it changes the size of the figure. So here's a non-rigid transformation. It's called a dilation. Okay, and you might remember if you've ever been to the eye doctor and they dilate your pupils, that means they make your pupils bigger so they can see farther inside your eye. But the shape of your pupil, the circle, doesn't change, but the size does. Okay? All right, so all the points are moved the same distance away from the center of dilation. You have to have a center of dilation, and all the points move the same distance away from that point, so that the remaining figure has the same shape again, but it changes size. Okay? So, we always have to have some kind of scale factor, and that distance away tells you what your scale factor is. Okay, so suppose if this is your original, and say this is 2 times that distance, then your scale factor would be 2. Because if this is x and that's 2x, then your scale factor is 2, because you're going twice the distance of the original figures. You're twice the distance from the center of dilation. Okay, so whatever that scale factor is, and we'll call it S, you're multiplying both of your ordered pairs by that scale factor. So that's how you can figure out what's going to happen to those x values and y values. But now keep in mind that the center of dilation might change what happens to those x and y values, because sometimes there might be some shifting depending on where that center of dilation is. And we'll talk about that more. All right, so let's take a look at a couple of examples. All right, first let's do a reflection. So we're just reflecting over this line of reflection. So we know we want to go perpendicular, the same distance away. 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 And then this one's going to be perpendicular, the same distance away. All right, so we've got this one, this one, this one. Here are all the points in the original, and we need to do that one, same distance away. So we have this point, this point, this point. Yeah, this point, and this point. So notice that all of these are congruent segments if you go from here to here and here to here. All right, so now we're just going to connect those with straight lines and see if our shape looks the same. It should. So if it doesn't, then we know something's wrong. All right, so does that look pretty close to what the original was? Yeah. So we've now reflected that over that line of reflection. Now let's take a look at a rotation. Okay, we want to rotate 180 degrees about this center of rotation. So 180 degrees gives us a straight line. So what we're going to do is we're going to draw a straight line through the center of rotation, the same distance away from that center of rotation. Okay, so here, this point gets mapped onto that point. All right, and now this point, we want to draw a straight line, gets mapped onto that point. This point will get mapped onto that point. This point gets mapped onto that point. And sometimes you might want to use colored pencils to keep your line straight. It's up to you. This point will get mapped onto that point. Let's see, we haven't done this one. So this point gets mapped onto that point. All right, so our new points are this one, this one, this one, this one, this one, and that one. All right, so then we're just going to connect them with a straight line. We'll use our green segment again. And we need to connect, actually let's use a different color. That'll help us to see it a little bit better. So we've got this connects to that, right? And then okay, and then this connects to that. And then this connects to that, and then that connects to that, and this connects to this one, and this connects to that one. Now, does this look like the same as the original? Yeah, and it's just been turned. So because it was 180 degrees, we're using straight lines. If it's 90 degrees, then that'll change things. You use a 90-degree angle that goes through that point, and we'll talk more about that later. All right, let's take a look at a translation. This one's kind of easy. Okay, so we're just moving all of these points 3 units to the right, and then that point goes 3 units. And now here's the tricky part, because I'm not very good at drawing semicircles. So let's take a look at this. First, we'll connect this. Okay. And now, here, you just do the best that you can. So we're gonna, should look something like that. Now again, it's not perfect because it's not a straight line. Figures that have all straight lines, polygons, are going to be easier to do. But that's just all of these points are translated the same number of units in the same direction. So if this were, say, F, then it gets mapped onto F prime, okay? And that is the vector that tells you the direction and the amount of, or the distance of that translation. All right, now let's take a look at the dilation. All right, the last one, dilation. Dilate the figure by a scale of 1/2, so we know it's going to get smaller, with the center of dilation at 4, 10. So we're going to go over to 4 and up to 10. So now what we need to do is draw our line segments from that center of dilation to each of the points. And then we need to find half of those line segments. Okay, so this one comes over 4, so we're going to go over 2. It goes up 10, so we'll go up 5, and there is half the line segment. You're just using your slopes. All right, so here you're going over 6 and up 2, so we're going to go over 3 and up 1. And for this one, you're going down, let's see, down 6, so we're going to go down 3, and over 4, I'm sorry, not 4, over 6, so we're going to go over 3. So each of those is half of that line segment, and then it's just a matter of connecting the points. So we will connect those, and you can see that this is the same shape as the original, but the size, it's half as big. Each segment is half as big as the original segments.